But if you try sometimes, well, you might find you get what you need.
As one adds randomly chosen securities to a portfolio, increasing its number, and we call that naive diversification because anybody can do it, the risk generally, not always, but generally does decline. And indeed, around 29 securities will get rid of about 95% of the diversifiable risk. We can show that mathematically, where the weights still add to 1, the return is still a weighted average, and the portfolio, we'll call this a matrix of n by n number of covariances, and they're weighted, and we can separate into those that are equal in terms of the horizontal and the vertical, and that's on the diagonal, if you will, and we see it's laid out here on this covariance matrix. And recall that the variance, where I equals j on the diagonal, is that special case and becomes then the variance. And if we examine the number of variances and covariances, we note that, well, there are n variances and n squared minus n, or if you like, n minus 1 times n covariances, and we let the weights equal 1/nth of the total portfolio, we find that the variance disappears as n gets large, and the remainder is the covariance. And this is contrary to what's found in most other statistics, whereby blind random sampling, the covariances are generally eliminated, and then they analyze the variances. In finance, we do the reverse. We get rid of the variance and examine the covariance, and as we will see, that's related to the market. And the average covariance is still composed of different pieces. Here, these red dots are firms that correlate to the market 1-to-1, might be General Motors, and these blue dots are something that goes up, say, 1/2 to 1 when related to the market. It might be, say, grocery stores or something less risky, and some are more steep. These green ones are something that has a slope of 2-to-1 to that of the move of the market. Maybe it's heavily leveraged or something more risky. And we have here those that are uncorrelated at all, have a 0 slope. These might be dairy farms. And note that's why we would think that these would get a return of the risk-free, because there's no risk. And then we have maybe a negative correlation, a slope of -1-to-1. These might be collection agencies, pawn shops, going up when the market goes down. As before, when we looked at a risk return measured in standard deviation and got the capital market line, let's do that again, but now with beta, because we can diversify, and that will create a risk-free return that has 0 beta. There's no correlation, no variance. And the beta of the market is 1. The covariance against itself. Here the market is the variance of the market, and mathematically in both versions the beta is 1, and that makes sense because the market goes up and down 1-to-1 with itself. And thus, if we graph this, the beta of 1 is associated with the return of the market, and we call this the security market line. The intercept of any linear equation is its intercept, here the RF, and the slope is the run divided into the rise here being that market premium, RM minus RF, and the run is 1, that's trivial from the beta of 1, and that gives us the slope of the market premium. And here let's look at their utility risk return preference, and again we like to be up and to the left. It may not be immediately obvious that the weights, while always adding to 1, don't have to be between 0 and 1. The blue dot represents a person who's 1/2 in the risk-free and 1/2 in the market. The red dot represents somebody who's borrowing on margin. Notice the weights still add to 1. You put, let's say, 1,000 in, that's your 100% weight. You borrow another 500, that's minus 1/2, and you take that 500 and buy another $500 or $1,500. That's going on margin. It's also true in the other direction. You could have a negative weight in the market Then again, you would start with 1,000. You would short the market. That's negative the market weight. And then you would take that extra 500, put it in the risk-free, and the weight for the risk-free is 1.5, and the weight in the market is minus 1/2, and that's called shorting. Well, it's time for a set of numeric examples. Here the risk-free has a return of 4%, beta is 0. The return to the market is 12%, the beta of course is 1, that creates the line. And A has an actual contract return of 9%, beta of 0.5. B, the green one, makes 18%, beta of 1.5. C is 19 and has a beta of 2. And here I'll show the calculations for A, the beta of 1/2, the correlation coefficient and the standard definition, and beta is the covariance, again divided by the variance of the market, and the computation of the variance of the market is 9, the 3 squared, covariance 4.5, we get 1/2 for the beta. And we can also use the other version, correlation coefficient times the ratio of the standard deviations. And a mnemonic trick here is that the I for the standard deviation goes on top, just as eyes do when I'm looking at you. Let's see if we drew our graph correctly with a mathematical check. The capital asset pricing model has the risk-free, the intercept, plus the beta times that market premium of RM minus RF. And A actually contracted out or achieved 9% with a beta of 0.5. And when we go to examine it, the market premium of 8 times that 1/2 is 4, plus the 4 of the risk-free gives us 8. But 9 is superior, we accept, and we call that kind of an investment below the market, but desirable, a cash cow. And B had an actual contracted achieved rate of 18, beta of 1.5, 1.5 times the premium of 8, plus the intercept of 4 gives us 16, but 18 is better, it's above the line, we accept it. Whereas on the other hand, C had an actual return of 19 and a beta of 2, and when we calculate it out, even though it was nominally better than all the others, it underperformed and we rejected it. Now here's where the stuff gets really good. A and B were both superior, but which one was relatively superior? A, we could have used margin, as you recall, by buying more than 100% of it, borrowing the rest from the risk-free, moving it out to the right. It would be along a slope here, if you will. And we could have maybe bought less than 100% of B, moving its risk to the left. That's called home brewed beta portfolio management. And what we're really doing is examining the slopes. And Trainer thought of this. You take the actual return minus the risk-free and divided by the beta. Just recall that's the slope. And when we do that for A at 9 and the risk-free at 4 divided by half, its slope is 10. And that's greater than the slope of the market, which again accepts it. And the actual return for B was 18 minus its intercept of 4 for the risk-free divided by its beta of 1.5, and we get a slope of 9.3, and that's greater than 8, but we accepted it again. But notice it didn't do as well, even though it was nominally higher. And if we go back and look at our accept-reject decisions based upon above the line, below the line, using the capital asset pricing model itself, we see that the accept-reject decisions are in agreement, which is the essence of the capital asset pricing model on Dr. C Invests.